Hello, everybody. Welcome back. Today we're going to be looking at Unit 7.4, which is all about taking those equilibrium constant expressions that we looked at in the last unit and actually putting some numbers to it and learning how to calculate the equilibrium constant expression. So get your calculators and let's get started. All right, so what you're seeing one more time is sort of the general expression for an equilibrium constant. Remember, guys, sometimes you'll see it just as K, sometimes you'll see it as K with a little subscript C. C stands for concentration. Sometimes you'll see K with a subscript EQ, and that EQ just stands for equilibrium. Okay. But if you'll recall, these brackets, of course, mean molarity. And what we're going to look at today is, plugging numbers in and actually calculating a value for that equilibrium constant. And as you go through more and more problems, particularly free response problems, you will notice that equilibrium problems will often include a temperature. Now, if you're looking at this, again, this equilibrium expression in orange up there, there is no place to plug in temperature. So it's not needed to calculate K, but it is an important feature of the problem. All right, and let's just briefly talk about why that is. So that K, that equilibrium constant, it's a constant, meaning it doesn't change, okay? No matter what you do to those concentrations of the reactants or the products, eventually when the reaction settles down, the value, once it reaches equilibrium, the value for K will always be the same, as long as the temperature remains the same. This is a really important concept. The only thing for a particular reaction, the only thing that can change the value for K, for a reaction the way it's written out, it's balanced equation, the only thing that can change it is temperature. And we're going to talk more about that in a later subunit, but I just wanted to highlight the fact that temperature is included in a lot of equilibrium problems because there will come a time when temperature does change and we have to figure out, how the equilibrium constant is going to be affected. So we're going to start off with a relatively simple question. I'm going to start it for you, and then I want you to pause your video and try it on your own. We're given a balanced reaction. It says the reaction above takes place at 300 Kelvin. Remember, as I said, temperature is very often given in these problems, and is allowed to reach equilibrium. The equilibrium concentrations of carbon dioxide and carbon monoxide are 2.5 molar and 0.35 molar respectively. You are asked to write the equilibrium constant expression for the reaction. Okay, guys, the word expression means without any numbers yet. Don't plug anything in yet. Just set up that expression. That's letter A. And then letter B actually wants you to plug in some numbers and find the value for K. So pause your video, give it a try. All right, let's see how you did. So the equilibrium constant expression looks just like that, okay? Now, remember, guys, let's review. We leave solids and liquids out of a Kc expression, so you'll notice that carbon solid has been left out of that expression. Okay, so we include gases and aqueous compounds only in a Kc expression. In letter B, we actually are asked to actually calculate a value for Kc. We're going to plug in those molarities that we were given, and we get the number 20.4. Equilibrium constants are typically expressed with no units. Okay, so that's always nice. That's one less thing you have to remember. So that was a pretty simple, straightforward kind of question. Let's look at one that's a little bit more complex. Okay, I know there's a lot written on this screen here. Okay, So I'm gonna move this guy over here so it's easier to see that whole chart. Okay, so but we're gonna break this down piece by piece. Don't be overwhelmed by how much is on the screen. So right at the top, I see that we have a balanced equation. It says solid carbon and carbon dioxide gas at 1160 Kelvin were placed in a rigid 2-liter container and the reaction represented above occurred. Okay, fine. As the reaction proceeded, the total pressure in the container was monitored. Results are recorded in the table below. Fine. Let's take this piece by piece, guys. Letter A says, write the Kp expression. Notice it doesn't say Kc, it says Kp. Okay, let's refresh our memories. If it's a Kp, P stands for pressure, what states of matter are to be included? Gases only. Okay, so let me come over here to a fresh screen. And for part A, okay, I'm going to write Kp equals, and let's go back. It's products over reactants. My product gas is carbon monoxide. And I'm not going to write brackets, guys, because these are pressures. So I'm going to write P, the pressure of carbon monoxide, and it had a coefficient of 2, so I'm going to square it, over the pressure, partial pressure of carbon dioxide. It had a coefficient of just 1, so it's just raised to the first power. So, ta-da, there is my answer for letter A, my Kp expression. Partial pressures are involved here. Okay, I left out that solid, that carbon solid. Let's look at part B. It says, for the reaction mixture at equilibrium at 1160 Kelvin, notice it's the same temperature as what was given originally. The partial pressure of carbon dioxide is 1.63 atmospheres. Calculate. Okay. Part 1 wants us to find the partial pressure of carbon monoxide. Okay, well guys, there's only 2 gases in this entire scenario, carbon dioxide and carbon monoxide. We are told the partial pressure of carbon dioxide, and they want us to find the partial pressure of the other one. Well, how do we do that? All right, well, it tells us that we are at equilibrium. So if you'll notice, look in the chart of data. Where has equilibrium been established? It looks to me, I'm looking at the total pressure of gases in the chart, it looks to me at the time of 8 hours is when equilibrium has been established. How did I know that? Because look, from 8 hours to 10 hours, the pressure remained the same. Okay, so that's an indication that equilibrium has been established. And look at the title of that column, total pressure of gases. So in part B, I know I'm at equilibrium, because it says for the reaction mixture at equilibrium, so I know where to look in the chart. I know what the total pressure is. It's 8.37. And I know the partial pressure of carbon dioxide. So all we have to do is subtract. This is going back to the gas laws unit, okay, where the P total, the total pressure, is going to be equal to the pressure of carbon monoxide plus the pressure, partial pressure of carbon dioxide. I know what the total is. Okay, we were given the partial pressure of carbon dioxide, so this is my unknown. Okay, if I subtract, I get this. Okay, final answer for that question. Okay, so let's see what else they want us to do. We're still under part B. This is part 2 under B, or letter B. Then they want us to calculate the value of Kp. Okay, well, let's come back. I know what my Kp expression is, right? So let's set this up. Kp equals the partial pressure of carbon monoxide squared. Well, guess what? I just found it right there. Don't forget to square it. And I know what the partial pressure of carbon dioxide is because they gave it to us in the problem. Okay, if I put that all into my calculator, and I'm going to round to 3 significant figures, I get 27.9 is my value for Kp. All right, last part. Part C says, in a different experiment at the same temperature, that's important, guys. Remember what we said. As long as the temperature stays the same, the equilibrium constant will be the same. So this Kp value that I just solved for in the problem above, I may have to use that number, and I can because I'm at the same temperature. The partial pressure of CO is now 5.31 atmospheres, so it's a different value. Calculate the partial pressure of CO2. Okay, fine. So 27.9, let's get to a new page. So 27.9 is my K value. Okay. Carbon monoxide is the one that is in the numerator. Let's see, was that the one I was given? Yes, 5.31. 5.31. And that's squared. And then this is my unknown. Okay, I don't know what that number is. All right, so we're going to do a little bit of algebra here. Let's get it out of the denominator there. So times partial pressure of CO2. So now my math looks like this. All right, and I'm going to go ahead and put that in the calculator. 5.31 squared. I'm not going to round too much because this is not my final answer. And I'm going to divide both sides by 27.9. Sorry if this is getting a little messy. So here is my final answer. And it's in atmospheres. Okay, so we used data that was given to us to find the value of the equilibrium constant, and then we used that number to calculate one of our partial pressures. Okay, and the reason I could use that same Kp value again was because they told us that we were at the same temperature. If the temperature was different, we couldn't use that number, and we'll talk in a later unit about what we would have done in that circumstance. Okay, but that is a little bit of a more challenging problem that you could see in doing these equilibrium constant calculations. Okay, the first problem we did was more simple. That one was a little bit more complex. All right. So I hope that you have learned a little something today, and I look forward to seeing you next time.